How does laser fusion works at the National Ignition Facility? Laser fusion, also known as inertial confinement fusion, is a process that attempts to replicate the conditions found in the core of stars, where nuclear fusion occurs naturally. This method utilizes powerful lasers to compress and heat small fuel pellets to extreme temperatures and pressures, initiating nuclear fusion reactions. The fusion process. Initial laser pulse. The process begins with the generation of laser pulses. These laser beams are amplified and split into 192 separate beams, each precisely aligned and timed. At the outset of a NIF experiment, a weak laser pulse, about 1/1,000,000th of a joule, is created, split, and carried on optical fibers to 48 preamplifiers that increase the pulse's energy by a factor of 10 billion to a few joules. The 48 beams are then split into 4 beams each for injection into the 192 main laser amplifier beam lines. Delivery to the target. The laser beams are directed through a series of mirrors and lenses, converging on the tiny fuel pellet in the target chamber. Guided by laser mirrors, LMs 1, 2, and 3, each beam zooms through 2 large glass amplifiers, first through the power amplifier, and then into the main amplifier. In the main amplifier, a special optical switch called a plasma electrode Pockels cell, PEPC, traps the light, forcing it to travel back and forth 4 times, while special deformable mirrors, spatial filters, and other devices ensure the beams are high quality, uniform, and smooth. Compression and heating. The laser beams strike the pellet's outer surface, creating an intense burst of energy. This energy rapidly heats and compresses the pellet, generating immense temperatures in the millions of degrees Celsius and pressures millions of atmospheres. NIF's laser beams can create nuclear fusion in the laboratory by generating the same kinds of temperatures and pressures that exist in the cores of stars and giant planets, and inside nuclear weapons. Fusion ignition. Under these extreme conditions, the nuclei within the deuterium and tritium fuel overcome their electrostatic repulsion and fuse together. This fusion reaction releases a substantial amount of energy, primarily in the form of high-energy neutrons and alpha particles, helium nuclei. The 7 wonders of NIF. Laser glass. Laser glass is the heart of the NIF laser system. It's the material that amplifies the laser light to the very high energies required for experiments. NIF's laser glass is a phosphate glass that contains neodymium atoms, Nd, glass. Neodymium-doped laser glass is the preferred gain medium for use in high-peak power lasers for fusion energy research. Achieving ignition, producing more fusion energy than the amount of laser energy delivered to the NIF target, provides new opportunities for stockpile stewardship applications and enhances the prospects for an inertial fusion energy future. Flash lamps. The amplifier slabs are surrounded by vertical arrays of flash lamps. Measuring nearly 180 centimeters, 6 feet, of arc length, NIF's 7,680 flash lamps are the largest commercial units ever made. Each is driven with about 50,000 joules of electrical energy. The flash lamps excite the neodymium in the glass slabs to provide optical gain at the infrared frequency of 1053 nanometer wavelength, also referred to as 1 omega. Optical switch. A key component in the laser chain, an optical switch called a plasma electrode Pockels cell, PEPC, was invented and developed at LLNL. A Pockels cell rotates the polarization of a laser beam when a voltage is applied across an electro-optic crystal. Depending on the voltage applied, the Pockels cell either allows light to pass through or to reflect off a polarizer, creating an optical switch. For each of NIF's 192 beam lines, a PEPC allows the laser pulse to make 4 passes through the main amplifier, building up its energy with each pass. Without this multi-pass configuration, NIF's beam lines would have to be much longer than they are. Preamplifier modules. NIF's master oscillator generates a very small, low-energy laser pulse. The pulse may range from less than 100 trillionths to 25 billionths of a second long, and has a specific temporal shape as requested by NIF experimenters. The low-energy pulse is split and carried on optical fibers to 48 preamplifier modules, PAMs, for initial amplification and beam conditioning and shaping. Deformable mirror. The computer-controlled mirrors serve as the eyeglasses of NIF. 39 actuators are attached to the back of the mirror. These mirrors push or pull the optical surface to correct optical distortion in the beam from residual thermal distortion, imperfect optical materials and surface flatness, and amplifier distortion due to flash lamp heating. By correcting each beam, a smaller spot size can be achieved, producing higher power density or better controlled focal spots at the target. With the help of deformable mirrors, beams can reach the required spot size of about 100 microns or smaller. That's less than the diameter of a human hair. Rapid growth crystals. The crystals serve two functions: polarization rotation and frequency conversion. KDP crystals are used in the plasma electrode Pockels cell, or PEPC, which allows light to either pass through or reflect off of a polarizer. By rotating the polarization of the laser beam, the PEPC directs the laser light back and forth through the main amplifier system for times, picking up energy with each pass. Then it is switched out to continue on its way toward the power amplifier. Computer control system. A NIF target shot requires all 192 laser beams to arrive within 10 trillionths of a second of each other, and to be aligned within 50 microns, half the diameter of a strand of human hair, all with the right frequency and energy level. It takes more than 66,000 control points to achieve this precision, as well as one of the world's most sophisticated computer control systems. More than 2,000 computers running 5 million lines of code make it possible to align and fire the 192 NIF laser beams with some 800 channels of target diagnostic data efficiently and reliably several times a day. The control system uses predetermined setup and alignment scripts with operator oversight, while test and full shot countdown sequences are fully automated. Laser fusion at the National Ignition Facility represents a monumental step in the quest for sustainable and clean energy. The advances made at NIF offer a glimpse into a future where fusion energy could transform the global energy landscape, providing a safe, sustainable, and environmentally friendly power source.